All right. Following the first video on the history of the atom, we just finished up going through Dalton's atomic theory and Dalton's atomic model of that like billiard ball type model. And now we're going to move into the three scientists primarily responsible for discovering the three subatomic particles. So up until Dalton, scientists believed that the atom was the smallest building block of matter, and it wasn't until the end of 19th century that J.J. Thomson and his colleagues came up with something different. For this video, I'm just going to kind of briefly cover the experiments and then the conclusions from those experiments that Thomson, Rutherford, and Chadwick conducted. But I am also going to link some really good videos from a YouTuber who's really awesome, who breaks these down in more detail and I think are super, super helpful. And I would highly recommend. They're not going to be required videos, but they are definitely recommended 100%. Would definitely give you a clear idea of the model of the atom and more on the experiments that led to them. So they'll also be provided on my website. Okay, so Thomson's plum pudding model. He was the first one who provided a hint that the atom is made up of even smaller particles. All right. He did this through his famous cathode ray tube experiment. So what he did, in a quick synopsis, is he had a glass tube, all right, like the images here, and it had a couple metal discs inside, and it was connected up to a power source, some kind of battery. So you can see like the wires with this cathode and anode ray, positive and negative ends of a battery. And he noticed at one end of the glass tube, he also had kind of like a screen where you could detect, you know, anything passing through or anything that happened once he connected the power source up. And what he noticed was that there was this ray, and it came from the cathode end of the battery, the negative end of the battery, so he called it the cathode ray tube. And so as the electrical current passed through the tube, he noticed that there was this ray. First, he didn't know what it was, but he decided he first put a like a positive and negative charged substance on both ends and saw which side the ray bent towards. And then he also put a magnet towards one of the ends to see if the ray did anything. I'm going to go back to his experiment a little bit more here, but based on the conclusions of this experiment, he proposed a new model of the atom. Okay, he proposed what's often called the plum pudding model. Plum pudding is a very famous British dessert. You might think of it more as like a blueberry muffin, okay, or like a fruit cake. And what he determined is that instead of an atom just being a solid billiard ball, okay, he thought that it was actually this dough-like substance that was primarily positively charged, but it had in it, like little blueberries in a muffin, were the sea of electrons, or electrons were scattered about like raisins in a pudding. Okay, so how did he come up with this idea? All right, so a little bit more on this was the conclusion of his experiment, but how exactly did he get here from that cathode ray experiment? So what he found was that this cathode ray, so it had this negative end, okay, and a positive end. And let me go back actually to this image. What he found was that if he had charged plates, okay, so if nothing was there on this tube, nothing would happen. But if you put a charged plate or a magnet, it would always bend towards the positive side. And if you remember, opposite charges attract, like charges repel. So if he had, if this is the positive end of a plate, it's a magnet, but just if it was a positive end, the ray would bend towards it. So he deduced that whatever was made up of this ray was negatively charged. Now, everyone believed at this time that atoms made up of everything. So these, he called them electrons. He deduced that they had to be coming from within the atom. So the atom couldn't be the smallest particle anymore. And so it's through this experiment that he came up with this plum pudding model. Okay, and I kind of like this image because it's three-dimensional. So imagine like a sphere, and this sphere is like a positively charged pudding or like dough with electrons scattered about, that when an electrical current passes through an atom, the electrons can just leave and form that kind of ray. All right, this is another little video that you could pause the video and watch this. I'll probably have a link to it on my webpage as well. Another one that just kind of goes through his experiment in a little bit more depth. But you want to know that J.J. Thomson is responsible for the famous cathode ray experiment, and that his plum pudding model is the first model of the atom that showcases a smaller particle than just the atom, which he called the electron. So here's his conclusion. He concluded that the negative charges came from within the atom. A particle smaller than an atom had to exist. So he's the first one to say that the atom was divisible. Remember, up until now, everybody said that the atom was the smallest piece of matter. He originally called them corpuscles. Today we call them electrons. And one little note, but he knew that the gas was neutral and that atoms in general are neutrally charged. Okay, so he knew that there must be positively charged particles in the atom, but he could never find them. He led the way for our next scientist, Rutherford. So before we can talk about Rutherford, I briefly have to introduce radioactivity on a very minute scale. Okay, so radioactivity on a very basic level is the spontaneous emission of radiation by an atom. It was first observed by Henri Becquerel. I'm not French, but that's his name. And then Marie Curie is the famous one who studied it, and her husband Pierre Curie. So lots of French people studying radioactivity. Marie and Pierre won the Nobel Prize in 1903 for their work on radioactivity. So what does this have to do with what we're talking about? So some atoms are unstable, okay? And radioactivity is the spontaneous disintegration, dissolvement of an unstable nucleus, and nuclei will randomly emit small particles called alpha particles, beta particles, gamma particles, okay? So in other words, elements can change into another element naturally due to unstable nuclei. Now that only occurs with very heavy elements above bismuth, number 83 on your periodic table. So they're the heavy elements that tend to be radioactive. Just a picture of Marie Curie here, and a nice quote from her. So Rutherford, his famous experiment is called the gold foil experiment, and we'll get to the conclusions of his experiment following. And he was an English physicist, and his work and his experiment at first seemingly had nothing to do with unraveling the mysteries of the atomic structure. Okay, so by this time, Rutherford was aware of 3 different types of radiation. He actually helped break them down. So there was a lead block with a radioactive substance. Radium was commonly used in this time. And there was a charged plate put on from the passing beam of whatever this radioactive substance was emitting. And they found that, okay, there were beta rays, gamma rays, and alpha rays. Now, based on what's attracted to what, if the beta rays are attracted to a positively charged plate, then they must be negative, because remember, opposites attract, and beta rays are in fact negative. Gamma rays don't seem affected by the plates. They have no charge. That is still true. And alpha particles are attracted to the negatively charged plate. And so beta rays are, or sorry, alpha rays here are positively charged, because remember, opposites attract. Beta rays are going to be your electrons being emitted. Gamma rays are no charges, high energy rays, and alpha rays are actually heavy, positively charged radioactive rays. We're going to focus on these alpha rays here. So, Rutherford's experiment involved firing a stream of positively charged particles at a thin sheet of gold foil. So he fired alpha rays, those positively charged rays, at a thin sheet of gold foil. Okay, so here's his radioactive sample, and it's emitting alpha particles. It's kind of like shooting like a laser gun at this gold foil, but the laser is filled with the positively charged alpha particles. Okay, and this is a zinc sulfide screen. All you need to know about that is it was a screen that was used to detect where the alpha particles hit. So Rutherford was really interested in, okay, he's shooting these alpha rays. Now, where are they going to hit on this detector screen? So he had predicted, he was actually a student of Thomson, and he was trying to prove Thomson's theory of the plum pudding model correct. And so he was expecting the rays to go through the gold foil undisturbed, and most of them did. However, some of the rays became deflected, and they deflected like just minorly, and some of them deflected quite severely, and some of them even shot right back at the source. It took him years to riddle this puzzle out, okay? So just so you know that the scientists didn't just like voila, one experiment, they knew everything was going on. But after years of doing this experiment and calculations and figuring it out, he came to some conclusions about the atom. So he was trying to prove Thomson's model, this model, right, this plum pudding model, this sea of positively charged pudding or dough with these negatively charged electrons. And so he thought that this dough or pudding was so light that the alpha particles would pass through seemingly unnoticed. And what ended up happening is most of them passed through unnoticed, but a couple of them were rapidly deflected or shot back at them. He described it as the same thing as shooting a gun at a piece of tissue paper and having the bullet fly right back at you. The results just didn't make sense with Thomson's model of the atom, so he had to change it. And so he came to develop what's called the nuclear model, or the model of the atom with the nucleus in it. These are a couple videos. This is like a interactive movie thing. You can look. They'll be linked on my page, but you can also look at them here if you want to pause the video and go look at them. Short little clips. Okay, so all of this, Rutherford reasoned that all of an atom's positively charged particles had to have been contained in a nucleus, not in a sea of pudding, okay? And that the negatively charged particles were scattered outside the nucleus around the atom's edge. So he reasoned that instead of it being a sea of positive with these electrons spread out throughout, that instead there was this dense nucleus. So Rutherford is responsible for the discovery of the nucleus, and around it electrons are just floating around, and they're attracted. Remember, opposites attract, so the positive nucleus, those electrons are attracted to it and stay relatively close to it. So he also reasons, because remember, most of the particles, most of the alpha rays passed through seemingly unnoticed. So here are a couple other conclusions from his work. Gold atoms and all atoms are mostly open space. Atoms are not a pudding filled with a positively charged material. He also concluded that an atom had a small, dense, positively charged center that repelled his positively charged bullet, those alpha particles. He called the center of the atom the nucleus. And it should be noted, that now we know that the nucleus is tiny compared to the atom as a whole. All right, the last one we're going to cover real quick here is the neutron. Okay, Rutherford's experiment had the most important consequences that led to the final mechanical model of the atom, the Schrodinger's model of the atom. But before that, okay, we have to go back. The one thing Rutherford couldn't puzzle out here was, okay, there's this dense positive center. How are the protons not repelling one another? Because remember, like charges repel. So he couldn't deduce how the protons could all be so compactly and densely in the nucleus of an atom. So here comes James Chadwick. This wasn't until 1932, okay, far after Thomson and Rutherford's work. So Chadwick and many other scientists had a hard time discovering the neutron. So why is that? Okay, one of the reasons is that neutrons have a special force known as the strong nuclear force that holds the protons together. It's actually the strongest of the four forces if you go and study physics, and it's like glue. Okay, it like glues the protons together. It's called quote unquote neutron glue. It's just a strong force, and it keeps those protons spaced out, but also in that dense center. So he did a couple of experiments. This is the video that I would highly recommend you go watch, the ones from the YouTuber. And basically, he also shot alpha particles at some other elements, but they weren't emitting a charged species of any kind. They were emitting something that was not charged. And through other deductions, he realized that it was emitting a neutron because it had mass and wasn't positively or negatively charged. He put it through plates, but it was big, and so it just took a while for the equipment to develop in order for them to conduct the experiments in order to prove that the neutron was there. But neutrons are also within the nucleus, and they help balance the repulsion of one proton to another proton within the nucleus, remembering that protons have the same charges, and so if there's more than one in a small space, they're going to want to repel, but the neutrons kind of get rid of that force and balance it out. So that's a summary of the main contributors to the subatomic particles. This is a very basic model of the atom. So if I kind of go back to the beginning of the slideshow, if we kind of look at where we're at, we have gotten through Dalton's, Thomson's, and Rutherford's model. We primarily have Bohr and Schrodinger left. So how does the simple Rutherford model in 1911 change to Bohr's and ultimately Schrodinger's, with, we're mentioned de Broglie here as well. That's what the next video will be covering.